Well, now let us see how to eliminate the edge responses. So for that we have to calculate the Hessian, which is calculated in this way as per this equation, where the x-axis is the derivative along the second derivative along the x dimension, then xy along the horizontal and vertical both dimensions, and then yy along the vertical dimension. Well, the trace of h is defined as per this equation, and the determinant is defined as per this equation, where alpha being the eigenvalue with a larger magnitude and beta being the eigenvalue with a smaller amplitude. Well, now this metric is calculated, and this metric can be simplified in this particular way if we make this substitution. Well, this is the the simple derivation based upon which I am saying this. So r plus 1 square divided by r. This is the equation now that we obtain. Now, the first case was the flat regions. So if the derivative magnitudes are very small, we know that the regions are flat. This is quite simple. The second thing is when we have the edges, at least one eigenvalue is supposed to be large as compared to the other eigenvalue. So this is how the edge responses look like. So in this case, one eigenvalue is very large and the other eigenvalue is very small. And if we analyze what is the case over here, well, if the value of r is either very small or very large, this means that the difference between the eigenvalues is very large. If that happens, then the magnitude value of this matrix is supposed to be large. Whereas if both the eigenvalues have eigenvalues are quite similar and they have a higher magnitude, then their ratio will be close to 1. Okay, so r should be somewhere close to 1. So we can always put a threshold on this particular value, that if it is less than a specific threshold, so this means that if the magnitude is larger than this value, then this means that it's not a flat region. If it is not a flat region, then we need to decide between the edge and the corners. For the case of corners, both the eigenvalues should be large. So this is what a corner is. Both the eigenvalues are large, and if both the eigenvalues are have relatively large values, so this metric will be greater than 0, but it will still be having a controlled value. The value will not be very large of this metric. So we can always apply a threshold to this value, that if this threshold does not exceed, if this value does not exceed this specific threshold, then we have a corner, and if it exceeds this particular threshold, then this means that we don't have a corner, but actually we have the edge, and we need to reject that edge as well. Now, going back and having a look at the overall procedure once again, just to recall, we have already done the first step, which is that we perform the scale space extrema, and based upon which we search over multiple scales and image locations, and based upon that we identify stable scale invariant points in the images. Then we have to do the key point localization. 2 steps had to be done for that. Number 1 was a scale space extrema, and number 2 was that we need to reject the edges, and we have done that using the Hessian and a particular metric. Now the third and fourth step are left. The third step is the orientation assignment. Now, in order to check or calculate this orientation assignment, we will quickly recall the slide that we have already seen in the previous lecture. That is the orientation normalization. This is how it is performed. I'm repeating this once again. So we need to compute our orientation histogram, select the dominant orientation, and then normalize the image by rotating the image patch by a fixed orientation. This can be done by first of all calculating or applying the filters along the horizontal and the vertical dimension. After we have done that, we can actually calculate the angle of the gradient, which is taken as the tangent inverse dy by dx, and we can also calculate the magnitude by taking dx square plus dy square root. So we have already seen this the last time. So this is how we can calculate the magnitude and the direction of the edges. Now once we have calculated the angles, we know that these are continuous values, and we definitely need to quantize these, and this is basically done by selecting an image patch, or if we are talking about a key point, and we select a specific region around the key point based upon which we have to calculate the dominant orientation. We filter the patch, we calculate the angles, and we calculate the magnitudes. Once we have calculated the angles, we can actually calculate a histogram of the angular displacements which are there in the image. We can generate this histogram by quantizing the angular axis between 0 and 180 degrees to maybe 5 or 6 discrete steps. So for example, over here we are going from 0 to 2 pi in 1, 2, 3, 4, 5, 6 and 7 different steps. So we can discretize all these angles between 0 and 2 pi, and then try to fix every angle to its particular bin. And once we have done that, then we can count how many pixels are there in every single bin. And if we see over here, this is the angular bin in which we have the highest number of pixels. So this is the dominant orientation, and if we need to perform any orientation normalization, it should be with respect to this particular angle. Now, once we are done with this step, we have basically four different the information at four different tiers. We have the x and y dimension of the stable point that we have found. We know the scale to which this point is sensitive, and we know the orientation of this particular point based upon the histogram that we have calculated, the histogram of local gradient that we have calculated. Now the next step is that we need to find the key point descriptors. So at this point we have each and every key point, and we have its location, its scale and its orientation, and the next step is to compute a descriptor for the local image region about each key point, that is number 1, highly distinctive, and number 2, invariant to as many possible variations as the changes in the viewpoint and illumination. So this is our objective function now. The next step is supposed to be normalization. So in this normalization step, we rotate the window to a standard orientation that we have already found based upon the information that we had. And the second step is that we need to find this, that we need to scale the window size based upon the scale at which the point was found. So we basically, if we have a key point, we have the scale of the key point, we need to find a window size based upon the scale of the key point, and we obviously need to rotate the window, that window by a specific angle that we have already found based upon the dominant orientation. And once we have done that, we have performed the normalization of the data that is there around the key point that we have already found. Last but not the least, we have to perform the Louis key point descriptor. Once again, the steps are mentioned over here. We use the normalized region about the key point in order to calculate this descriptor. We compute the gradient magnitude and orientation at each point in the region, and we weight them by a Gaussian window overlaid on the circle. Now the reason of using the Gaussian window is that it is going to smooth out the image and remove noise, because the gradients occurring at the individual pixels can have noise, even the sensor noise because of the camera or the imaging device, and therefore we weight them by the Gaussian window to remove the effect of noise. And then we create an orientation histogram of most importantly 4x4 subregion of the window. We are talking about the Louis key point descriptor. So in the Louis key point descriptor, an orientation histogram of 4x4 image subregions are basically created. And now in order to calculate a descriptor at a key point, we basically pick 16 by 16 regions from the images, 16 by 16 regions from the images, and these 16 by 16 regions in the images are divided into 4 by 4 regions. So in essence we will be having 16 regions in the image. So from these 16 regions, we calculate the orientation histogram, and as far as the resolution is concerned, for the low key point descriptor we are keeping a track of 8 different directions. So 16 different image patches of size 4 by 4, and for each image patch we calculate an 8 bin histogram of the dimensions. So for each and every single key point we will be having 16 multiplied by 8, and it gives us 128 values of one particular key point. This is important. So for every key point we get 128 different values as a descriptor, and these are the descriptors that we are looking for. Most importantly, before the calculation of the descriptor, the region was normalized based upon scales and based upon the orientations. Well, in conclusion, there are a lot of uses of Sift. The feature points that we have extracted from Sift can be used for image alignment. We can use 3D reconstruction. We can do motion tracking. We can do object recognition, indexing, and database retrieval. And there are lots of hundreds of other applications for which Sift has been found to be very useful.